Okay, so example 9 deals with another favourite type of question, and that's the hinge. So a hinge is generally used when something's attached to a wall, and the hinge allows the rod to turn, but it doesn't allow that point of the rod to move. And often to do that, it will need to use a reaction force. So on top of the normal sort of reaction force that you get off a surface, a hinge can give you a reaction force in any direction at all, because it's fixed in place. So if I try and pull it away from the hinge will resist the movement in that direction. If I try and push towards the hinge, the wall will give me a reaction force to resist me pushing towards. So whatever I do with my rod, the hinge is going to oppose that and is going to make sure that we stay absolutely put at this point. That's sort of the general explanation. What does it look mathematically? How do we set up a hinge question? What forces do we put in? Well, we start off with a wall. So we've got a wall here. And then we draw in the rod, and it tells me in this one, the rod is going to be equally in a horizontal position. So we've got a horizontal rod coming out here, and this is A, B, and so the hinge point will be here. So let's just finish the rest of the setup. It's uniform, its length 4 meters. So hold on, let's just see. The string is attached to point C where AC is free. So there's going to be a string 3/4 of the way along, which we'll call C, and to a point D vertically above A. Okay, so here's our string up here. So that's attaching, and that's stopping the rod falling. So here we've got a hinge. So if we imagine the rod can move this way or it can move this way along there, and there's a string stopping it from falling down. So if we begin to mark on all the forces, we've got the tension force. It tells you that it makes 40 degrees, the string and the rod here, 40. And then we've got the force straight down, which is going to be 6 kilograms, so 6G, and it's uniform, so it's in the middle. So 6G in the middle. And then we've got some lengths to put in, so the whole thing is 4, this is 2, this is 3 meters from A, so this makes that 1, and this is 1 here as well. Now I've almost finished, we just need to deal with the hinge assumption. So that's what they've described there in terms of the picture. And the hinge assumption gives us that the force can be in any way that's required to keep this stationary at this point. Now, and stop it moving up or down as well. So what I'm going to do, the easiest way to do these hinge questions, rather than drawing a force at an unspecified angle, is I'm going to split it into 2 elements. I'm going to have a vertical force, so I'll call this Ry, and I'm going to have the horizontal force. So although in fact it's one force, I'm going to think of it as already split into horizontal and vertical components. That's going to make it easy for us when we try and resolve in the different directions. And that's all because it's hinged. So a hinge stops movement and will put reaction forces in place to make sure there is no movement at that point. That point A cannot move. The metal hinge, you imagine it, is fixing it in place, and there can be a reaction force in any direction that requires that to be necessary. Okay, so let's have a look here. We've got the same options, so we can resolve vertically, we can resolve horizontally, and we can take moments. So let's just do them one at a time, right? Yeah, if we're not sure what to do, it doesn't matter the order we do them all, and we get some equations. So resolving vertically, and this is why I chose 2 forces, right? So we've got pulling it up is Ry plus, and then this T is going up, it's not going directly upwards, so we have to resolve to the vertical, right? It'd be there, so we're going away, so it's T sine 40, and that's equal to the 6G pulling it down. So I've got 2 unknowns there, Ry and T, so that's not a lot of use at this stage. If we do it horizontally, we've got the Rx pulling it to the right, and then the T pulling it left, and they're the only 2 forces, but this time it's T cos 40 because we're going through. And again, 2 unknowns, T and Rx. And they're different unknowns, so I can't solve them simultaneously. So what we must do to proceed is to take moments. We've not got enough information from that, so move on to the moments. And again, we want to take moments at the point where the most stuff that we don't know is, which is going to be A. Moments at A, we've got it's being pulled down clockwise by this one, and it's being pulled up anti-clockwise by that one. So the clockwise is going to be 2 is the distance and 6g. That's already perpendicular, so I don't need to resolve it. So 2 times 6g is 12g, and this is a clockwise force. Meanwhile, right, our tension is an anti-clockwise force, and it's a distance of 3. So 3 times t, it's not perpendicular to the rod, so I must resolve sine 40. And this is 3t sine 40 anti-clockwise. And then, of course, they must be equal, right, because we're in equilibrium. So 12g equals 3t sine 40. And finally, you've got an equation that only has one unknown, the tension. So I divide by 3 and sine 40. So 12g over 3 sine 40 will give you the tension. This is 17 Newton, no sorry, can't read my calculator, 61 newtons to 3 significant figures, which is brilliant. That's part A, but it's also going to allow me to do part B, because it asks for the magnitude and direction of the force exerted on the rod by the wall. So if I can get Rx and Ry, I can work out what the magnitude is of that and which direction it's acting in. So let's do that now. I've got tension, so I just substitute into each of those. So let's do the first one. I've got that Ry equals 6g minus 61 sine 40. I'm going to use my full accuracy though on my calculator there. For my 61 value, it's not actually 61. That's a rounded. This gives you 19.6 newtons, right? Meanwhile, I can do the other one, which is the Rx, and that's just t cos 40, so 61 cos 40, which is 46.7 newtons to 3 significant figures. Now, both of those have come out positive, which means that they're moving in those directions. It's entirely possible, though, that they could be moving, the Rx could be going to the left and the Ry could be going down, depending on the values of these forces here. So we wouldn't know that, but we would see here because we would get a negative answer. So if my Ry was negative, I would know in fact I was going down. So when I draw my diagram after this, I would draw it in the downwards direction. So we don't know which way those reaction forces are going, whether they're to the right or to the left, to up or down, but we do know here because they'd be negative if they were going in the opposite direction. It doesn't ask us for the two components of the force, there it asks us for the overall magnitude and direction. So go back to drawing our force diagrams at a much easier time in mechanics. So I've got an Rx, so if I think about point A and what's going on, and this is the point at the wall where the rod's contacting the wall, I've got a force of 46.7 going this way and a force of 19.6 going this way. So if I want to find the overall magnitude and direction, well, here's my magnitude of the force, right, and here is my direction. So to find the magnitude, we're going to use Pythagoras. So the magnitude is 46.7 squared plus 19.6 squared, all square rooted. So again, use my full calculator accuracy though, and I get 50.7 newtons to 3 significant figures. So that's the force of the hinge, the reaction force to stop that rod moving is 50.7, and what direction is it acting in? Remember, it can act in any direction that it needs to because it's a hinge. So the direction is equal to tan inverse of 19.6 over 46.7, which gives me 22.8 degrees, right? And we just have to specify what that's in regards to. So this is 22.8, and that's above the horizontal. Yeah, it's no good just writing 22.8 because we have to have some sort of reference point so we know what's going on. Alright, that's hinges, and the key point, a force can be acting in any direction, so the best way to do it is to take two components, the x direction and the y direction, for our reaction. That's lesson 4 done, which means your turn to do exercise 7D. Have a go at the odds. There's loads of questions in there, right? It's tricky, I know it's tricky. Certainly I'd say this is the single hardest lesson that you're going to do in mechanics in the A-level course. So watch the examples. I know they've been long, re-watch them. If there's any questions, post them on the forum, and then have a go at those exercise 7D odds. Use the work solution to help you if you're struggling.